Hello friends. Today we are going to discuss the inner automorphisms. So what is a group automorphism? The group automorphism is a group isomorphism from a group onto itself. Informally, it is a permutation of the group elements such that the structure remains unchanged. Or else I can say an isomorphism is also known as an automorphism if both domain and the range are equal. It is actually a bijection from a group onto itself that preserves the structural properties of a group. Actually, the identity map is mapped onto itself. So today, let us discuss the inner automorphism of a group. So here are objectives of this lecture is to discuss the inner automorphism with related theorems and examples. So in group theory, an inner automorphism of a group is given by the conjugation action of a fixed element in the group. And this is realized by simple operations within the group itself. And that is the reason for the word inner. In this module, we will define inner automorphism, self-conjugate element, center of a group, and automorphism group. So these are the topics or else the outline of this lecture. Now, let us go to the definition. You can see the screen. So we'll go to the definition of inner automorphism first. Let G be a group and let G be a fixed element in the group. Then the mapping TG on G, which is defined as TG of X is equal to GX G inverse for all X in G is called the automorphism of G. And it is called the inner automorphism. As discussed, the word inner is because this action is realized by the simple operations within the group itself. So here the definition, you have to see the definition. It's a function defined as GX G inverse, where G is a fixed element of the group. So such an automorphism defined on a group is called the inner automorphism of a group. So let us go ahead and see the proof. As you all know, whenever you have to prove that it is an automorphism, first let us prove it is an isomorphism. Automorphism is nothing but an isomorphism on a group. So in order to prove that a function is an isomorphism, we need to prove that the defined function is one-to-one or else injective, and it is onto or surjective. That means the given function is one-one and onto, that it is bijective map. And also you have to prove that it is a homomorphism. So a one-one onto map, which is a homomorphism on a group, is called an automorphism. So if it is defined from a group to another group, then you call it an isomorphism. And when it is defined on a group, you call it an automorphism. So first, let us prove that it is a one-to-one mapping. So how do you prove that a given map is one-to-one? See, what you have to prove is, suppose we have a function f on a set X. So in order to prove that it is one-to-one, let us take two different elements of X, X1 and X2. And the conventional way of proving it is that if f of X1 is equal to f of X2, then prove that X1 is equal to X2. That means no two different elements are mapped down to the same element. This is what you mean by a one-to-one mapping. So let us start. Here the function notation is t suffix g. So in order to prove that t suffix g is a one-to-one mapping, we are taking two elements, say x1 and x2 in the set G. So let's assume that tg of x1 is equal to tg of x2. So by definition of the function tg, it is gx1 g inverse is equal to gx2 g inverse, because we have defined the function tg as gx g inverse for a fixed element g in the set G. Now we get the equation gx1 g inverse is equal to gx2 g inverse, and since you know that G is a group, we have the inverse of G existing, where G is a fixed element of the group G. So we can pre-multiply with G inverse and post-multiply with G, whatever be the operation of the group. So if star is the operation, we can apply the operation by taking G inverse, that is pre-multiply with G inverse using the operation star, and post-multiply with G by taking the operation star. Now, if I do so, we have G inverse of gx1 G inverse G is equal to G inverse gx2 G inverse G. So since associative property holds for a group, G inverse G can be clubbed together or associated together for the operation. So G inverse G becomes the identity element E, because identity element exists, and also now E star X will become X. So using two properties, the associativity, the existence of inverse, and the existence of identity of a group, we prove that x1 is equal to x2. It's a very straightforward proof. So we get TG is a one-to-one mapping. So one part, that means we have proved that the function is injective. Now we have to prove that the function is onto or surjective. For that, we have to prove that the range is equal to the codomain. So we take any random element in the codomain and prove that there exists a pre-image in G for that element. So now let us choose an element Y in G. Here the domain and codomain is the set G itself. We are discussing automorphism here. So for any Y in G, we can find an element G inverse Y in G, because G is a fixed element in G which we have chosen for the definition of the function. And since G belongs to G and G is a group, G inverse exists. So G inverse Y also should exist in G. So let us see what its image is. So TG of G inverse YG is equal to, by definition, it is G into that element, that is G inverse YG into G inverse. So again, using the associative property, G inverse can be associated, which reduces to the identity element, and we get it as Y. So for any element Y, we get a pre-image G inverse YG, which is also an element of G. Because since G is an element of G, the group G, we have G inverse belonging to G and also Y belonging to G. Hence, we get the pre-image as G inverse YG, and it is clearly an element of G. Now we have proved that it's a bijective mapping. Now what is left with us is to prove that it is a homomorphism. So in order to prove that it is a homomorphism, we have basically what we are doing is the structure is being preserved. That is what we have to prove here. It's from a group G onto itself. So if star is the operation, we have to prove that TG of X star Y is equal to TG of X star TG of Y. So if we consider X and Y belonging to G, clearly XY should belong to G because of its closed property. Now let us see what its image is under TG. So Tg of xy is G into xy into G inverse. Now what we are doing is we are multiplying an element G inverse G which belongs to G, that is the identity element. So you can write xy as xey. So E can be written as G inverse G. So then we associated Gx G inverse and Gy G inverse. So clearly by definition of the map Tg, Gx G inverse is Tg of x and Gy G inverse is Tg of y. So this is how we prove that it is a homomorphism. Hence, what we have done here is we have proved that Tg is a one-to-one onto homomorphism. That means it is an automorphism of G. And the set of all inner automorphism of a group is denoted by capital I of G. That is, I of G is the set of all Tg. That's the automorphism of group G, where G is a fixed element of G. That is, all the set of elements would be of the form Gx G inverse for a fixed element G in G for all x in G. So here, since Tg is an automorphism of G, defined with respect to a particular element or a fixed element of G. So you can consider it as a special kind of an automorphism known as the inner automorphism. So the next definition that we are going to is the self-conjugate element. We'll stop this session with this the definition. So self-conjugate element is, suppose we have a group G, an element A in G is said to be